Hello, I'm Norman Wildberger. Today we're going to look at another important application of linear algebra to polynomials and sequence spaces. So what we're going to do now is shift our attention from polynomials as functions to polynomials interpreted as sequences. Here's a typical polynomial that we're looking at. It's a formal expression involving linear combinations of power of some variable alpha. This particular polynomial happens to be in P3, our favorite polynomial space of all the polynomials of degree 3 or less. And we've seen how this polynomial can be interpreted as a function on the rational number line, which we can graph in the usual way. And the techniques of calculus apply to functions like this, and so the calculus and the polynomials interact. Today we're going to look at a quite different interpretation of the same polynomial. We're going to think of this as representing a sequence P of n, which is P of n equals n cubed minus 2n squared plus n plus 1, where n is now an integer. So we're only going to be considering values when n is an integer, 0, 1, 2, 3, and so on in that direction, and also minus 1, minus 2, and so on in that direction. So for example, when n is equal to 0, we evaluate to 1. When n is equal to 1, it evaluates to 1 as well. When n is equal to 2, you can check it evaluates to 3. When n equals 3, it evaluates to 13, and we could continue on in this way. Negative values are also possible. At minus 1, it's minus 3. At minus 2, it's minus 13, and so on. So this is a sequence, but it's kind of a two-sided sequence because it goes off both in this direction and in this direction. Sometimes we might want to only restrict it to positive values, or perhaps even to values strictly greater than 0. Now this is a kind of a side of mathematics that's not as studied as much as the calculus side in undergraduate mathematics, but it's probably just as important. Functions and sequences are kind of complementary, continuous versus discrete. In the last few decades, the importance of discrete phenomena has increased. And now we can appreciate that there's a lot of very interesting sequences. There are probably many more interesting sequences than there are interesting functions, to tell you the truth. In any case, we want to balance our point of view, so we're going to be studying polynomials interpreted as sequences. So this is in keeping with an expression-oriented approach to mathematics. In the 20th century, mathematics was focused on objects. I believe in the 21st century we're going to make a transition to not focusing so much on objects, but rather on expressions. Because it turns out that we can be much more precise and careful with expressions than we can with objects, and there's a kind of a flexibility by thinking of an expression like this as not necessarily being a function, as not necessarily being a sequence, but as incorporating those possibilities along with perhaps many others. So let's have a look at sequences today and some interesting analogs of calculus that apply to them, all from the linear algebra point of view. So let's start by looking at some very simple sequences and then work our way up to some slightly more complicated ones. Here is our basic reference frame of the integers. These are the labels that the sequences are going to be indexed by. Here's a name of a polynomial, and here is the corresponding sequence which it generates. So the polynomial 1 generates the simplest non-zero sequence, the sequence which is all ones. The polynomial alpha corresponds to the identity function, the function that inputs an integer n and outputs n. So its values just mimic the values of the labels n. Here's alpha squared, which represents the function or the sequence n squared. 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. And here's minus 1 squared, minus 2 squared, minus 3 squared. And here's alpha cubed, representing all the cubes. 0, 1, 8, 27, 64, and so on. And clearly we could carry on like this. These are the ordinary powers, the basic building blocks for a polynomial, interpreted now as sequences rather than as functions. Okay, one of the novelties of thinking about sequences is that there are other important bases for sequence spaces other than the power polynomials. And now we're going to introduce the most important ones. They're called factorial powers. And we're following the very important and interesting suggestions by the eminent computer scientist Donald Knuth, who proposes that we consider two types of factorial powers, so-called lowering and raising powers. So let me explain what that notation is. It's a very useful notation and it's very important. So let's start with alpha to the 2 falling. It's a falling factorial power. And what this is defined to be the polynomial alpha times alpha minus 1. So there are two things being multiplied together. If it was an ordinary power, it would be alpha times alpha. But it's a falling power represented by that little bar under the 2. And so we take alpha times alpha minus 1 instead of alpha times alpha. Well, alpha times alpha minus 1 is also alpha squared minus alpha. So this expression is nothing but another way of, or a shorter way of writing the polynomial alpha squared minus alpha. And here are the values of the corresponding sequence. So for example, if we want to evaluate it at 2, we have to take 2 times 1, which is 2. If we want to evaluate it at 3, we have to multiply 3 times 2, which is 6. So please check that those are the values for the sequence associated to our falling power alpha to the 2 falling. Here is alpha to the 2 raising. Its definition is over here. So it's like alpha squared, but there's a bar above the 2, telling us that instead of taking alpha times alpha, we're going to take alpha times alpha plus 1. We're going to go up. Well, alpha times alpha plus 1 is alpha squared plus alpha. And so the terms are like this. For example, at 3, you'd calculate 3 times 4, giving you 12 there. Now there's a kind of an obvious correspondence between this raising power and this lowering power. They're really almost the same, except they're just shifted by 1 as sequences. Okay, what about a third power? So here's alpha to the 3rd lowering power. Alpha to the 3 lowering is alpha times alpha minus 1 times alpha minus 2. And that expands as this polynomial, alpha cubed minus 3 alpha squared plus 2 alpha. And while we're at it, the raising power, alpha to the 3 raising, is alpha times alpha plus 1 times alpha plus 2, going up. But still 3 things being multiplied together. And that's the polynomial alpha cubed plus 3 alpha squared plus 2 alpha. And as sequences, here are the corresponding sequences. So for example, for the alpha 3 lowering, so the value at 2 would be 2 times 1 times 0, which is 0. The value at 4 would be 4 times 3 times 2, which is 24. The value at minus 1 would be minus 1 times minus 2 times minus 3, which is minus 6. And there's alpha to the 3 raising. So these are alternate polynomials. They're a little bit more complicated than the ordinary powers. Instead of multiplying lots of alphas together, we're multiplying alpha times alpha plus 1 times alpha plus 2, or alpha times alpha minus 1 times alpha minus 2, and so on. But there's a very good reason for studying these polynomials. These polynomials are very important when it comes to understanding sequences. All right, so let's make sure that we understand the definitions of these lowering and raising powers. So alpha to the n lowering is alpha times alpha minus 1 times alpha minus 2, all the way up to alpha minus n plus 1. And this index guarantees that we've actually got exactly n terms here. If there wasn't this 1 here, then there would be n plus 1 terms. But we really want n terms because we want it to be like a power, n things multiplied together. It's just that they're not all alphas. They're alpha times alpha minus 1 times alpha minus 2, and so on. So it's much like a factorial. Like 5 factorial is 5 times 4 times 3 times 2 times 1. It's very much like that. And here's the raising factorial power, alpha to the n raising, which is defined to be the polynomial alpha times alpha plus 1 times alpha plus 2, all the way up to alpha plus n minus 1. Again, exactly n things being multiplied together. Now there's an important relation between these two things. They're quite close. And we can see the connection by thinking about what happens if in one of them we replace alpha with minus alpha. So suppose in this lowering power we replace alpha with minus alpha. So there will be a minus alpha here. There will be a minus alpha minus 1 here, which is just the negative of that term. And then the next one will be minus alpha minus 2, which will be the negative of the alpha plus 2 there. So each one of these terms here will be exactly the negative of exactly these terms. That's telling us that minus alpha to the n lowering is alpha to the n raising multiplied by either plus or minus 1. In fact, minus 1 to the n, because there's 1 minus 1 term for each of these n terms. And it works completely symmetrically. If in alpha to the n raising we replace alpha with minus alpha, then this becomes negative of that. This minus alpha plus 1 here is exactly the negative of this one, and so on. So exactly the same relation holds, that minus alpha to the n raising is minus 1 to the n times alpha to the n lowering. And let me emphasize that all of these objects, they are polynomials. They're formal combinations of powers of alpha once you expand them all out. You can always expand them out and get something involving powers of alpha, alpha squared, alpha cubed, and so on. So now let's try to figure out, why do we want these raising and lowering factorial powers? And a good way of seeing where they come from is to talk a little bit about general sequences. So let's have a look at a rather interesting sequence. This one right here. The sequence that starts off 1, 5, 14, 30, 55, 91, 140, 204, 285, 385, and so on. The natural question is, what is the pattern? How does it carry on? What's the next element in the sequence? Well, if you know about the online encyclopedia of integer sequences, you'll know that this is an easy question to answer. You go online, you Google these terms, you get to Neil Sloan's fabulous compendium of integer sequences with thousands, tens of thousands of interesting sequences in it. And if you give it, say, the first 5 entries there, it will quickly tell you that this is sequence A000330. That's just Sloan's name for this particular sequence. And these are the square pyramidal numbers. What does it mean? Well, they have a number of different interpretations. They can be interpreted in terms of the number of vertices in a kind of a pyramid of a certain size. Perhaps the simplest interpretation is in terms of a square. If you take a square, in this case 2 by 2, and ask yourself, how many squares are in that picture? How many squares do you see? Well, we see that square, that square, that square, that square. There's 4 little squares. But suppose there's also the one big square for a total of 5 squares altogether. Now, if I asked you the same question for a 3 by 3 square, you'd say, you can count them, and you would find out that there are 14 of them. So that's one possible interpretation of what this sequence is. It's the number of squares that you can find of all sizes in a large square, which is sort of n by n. Now suppose that we didn't know this. Suppose we were working 30 years ago when this online resource wasn't available. How would you analyze a sequence like this to try to figure out what the next pattern is? Well, there's a tried and true method that goes back at least to Newton, probably goes back to the ancient Chinese or Indians or someone. It's a very natural idea. The thing is, you just look at the sequence and you ask yourself, well, what's the difference between successive elements? And let's write down below each element here, we'll write down the difference between the next one and the element that we're underneath. So 5 minus 1 is 4. There's a difference of 4 going from here to here. There's a difference of 9 going from here to here. Difference of 16 from here to here. Difference of 25 from here to here. And so on. Now most of you will recognize this sequence here, but suppose that you didn't. And suppose you said, well, what's the pattern here? Well, again, you could say, well, let's look at the differences. What's the difference between 4 and 9? It's 5. The difference between 9 and 16, it's 7. The difference between 16 and 25, it's 9. So there are all the differences between these ones. Well, it's pretty obvious now what the pattern is, but if you didn't know, you could take, well, the differences between these successive ones, which are all 2s. Now it's completely obvious what the pattern is, but if you did it one more time, then there would be all differences of 0s, and then from then on there wouldn't be anything else to do. So we can use this information. As soon as we have one of these rows, we can fill what's going on with the row above it. So for example, once we know this is 100 from here to here, and we know what this pattern is here, we know the next one is the next square, 121, then it means that the difference between the next one and this one must be 121. So if we just take this element and we add 121 to it, we're going to get the next element in the sequence. And that's 506. And if we hadn't known what the pattern was here, but we had known what the pattern was here, then we could use this difference level to work out what the next element in this difference level was. And then we could use that one to work out what the next element in the original sequence was. This is called a table of forward differences. And it's an important way of analyzing sequences. There are actually 2 different ways of working out these differences. And so mathematicians have devised 2 different so-called operators, which take a sequence and calculate the successive differences. So the 2 operators are this triangle here and this upside down triangle. There's symbols for them. And they're called the forward difference operator and the backwards difference operator. So let's see what these things do. These are operators on polynomials. So they're something that input a polynomial p and output another polynomial. And what is triangle of p? Well, triangle of p is a polynomial whose value at alpha is obtained by taking p of alpha plus 1 and subtracting p of alpha. That's sort of what we're doing with the differences. We're taking the n plus first element and subtracting the nth element. Here we're doing it at the level of the polynomials, not at the level of the sequences, however. And this other one, let's call it del p of alpha, is the difference between p evaluated at alpha and p evaluated at alpha minus 1. It's called a backwards difference. So let's do some examples. Let's look at the polynomial alpha cubed. What happens if we apply the forward difference operator to it? Triangle of alpha cubed. That's the polynomial alpha plus 1 cubed minus alpha cubed. We know how to expand alpha plus 1 cubed using the binomial theorem. When we do that and subtract alpha cubed, then what's left is 3 alpha squared plus 3 alpha plus 1. So that's what the forward difference operator does to alpha cubed. It sends it to this one. What about the backward difference operator, say evaluated at alpha to the fourth? According to the definition, it's alpha to the fourth minus what you get when you replace the alpha with alpha minus 1. Alpha minus 1 to the fourth. Okay, so you can also use the binomial theorem there to expand alpha minus 1 to the fourth out. Take this minus that. The alpha to the fourth terms will drop out, and you'll be left with 4 alpha cubed minus 6 alpha squared plus 4 alpha minus 1. We can apply these operators not just to individual powers, but to more general polynomials. And when we do that, we use the linear property so the triangle evaluated at this polynomial here is the same as the triangle evaluated at alpha cubed plus 2 times the triangle evaluated at alpha squared minus just the triangle evaluated at 1. This is a linear operator on polynomials. So we've calculated triangle of alpha cubed right there. Triangle of alpha squared would be alpha plus 1 squared minus alpha squared, which is 2 alpha plus 1. So we have to multiply that by 2. And then triangle of 1 is the value at alpha plus 1 minus the value at alpha, which is 1 minus 1 or 0. So we add these all up and we get 3 alpha squared, 3 alpha plus 4 alpha is 7 alpha, 1 plus 2 is 3. So there's the forward difference operator applied to this degree 3 polynomial, outputs this degree 2 polynomial. So suppose that we're given our sequence, perhaps the sequence of square pyramidal numbers there. And we want to analyze that sequence by taking successive differences. We have 2 possible approaches. We can take forward differences, or we can take backward differences. They are both roughly equivalent, and it's a matter of taste and sometimes of convenience which one we're going to choose. Our notation will be that we're going to think about the forward differences in a table below the sequence and backwards differences in a table above the sequence. That's just one way of keeping straight in our minds what kind of difference table we're looking at. So below the line here, that's what we already talked about. The difference here, this 4, is the difference between 5 and 1. This is a forward difference because it's the value of the sequence at this point and the value at the sequence at the next point, the difference of those two. So these here are the values of the forward difference operator acting on that initial sequence S. And here's our notation for the forward difference of the forward difference. There's the sequence of forward differences. Here is the sequence of forward differences of that forward difference. 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16 is 9, and so on. And we could carry on. Triangle cubed of S, triangle to the fourth of S, successive further forward differences. Something else that we could do is we could look at backward differences. Okay, so what happens there? So there, at some point, say this one here, we're looking at the sequence at that point minus the sequence at the previous position. So 5 minus 1 is 4. That's why we put a 4 here. The backward difference at this point is the value here minus the previous value. That's 9. 30 minus 14 is 16, and so on. So this is the sequence of backward differences of S. The upside down triangle, or what we're calling del. That's a del operator, del of S. And we could take the backward differences of the backward differences. That would be del squared. And so we would write it here because this thing here represents the difference between this value and the previous value. So we put it right up over the value that we're at. The difference between here and here is the 7. The difference between here and here is the 9, and so on. So the forward differences are all kind of lined up on this side, while the backward differences are sort of lined up on this side. And here they're kind of going up on a diagonal, and here these ones are going down on a diagonal. So it's a convention. It allows us to keep the forward differences straight because they're always going to be below our sequence, and backward differences above the sequence. Okay, so now that we've got some notation, let's have a look at why these lowering factorials and raising factorials are interesting and useful. So the key insight is that when we're looking for difference operators are especially easy to evaluate when we're talking about lowering and raising powers. They're easy to compute. And now I'm going to show you exactly why that is. So we're going to look at this particular lowering power, alpha to the 3 lowering. So we're going to take that particular polynomial and we're going to apply the forward difference to it. We're going to think of it as generating a sequence, and we're going to take that forward differences of that sequence. So what's the definition of the forward difference operator? The definition is that we take this polynomial and evaluate it first at alpha plus 1, and then we subtract the value at just alpha. Okay, so what is alpha plus 1 to the 3 falling? It's alpha plus 1 times alpha minus 1. And what is alpha to the 3 falling? It's alpha minus 1 times alpha minus 2. Now have a look at these two terms. There's a common factor of alpha times alpha minus 1 in both terms. And what's left over, if we take out that common factor, is an alpha plus 1 from this term and a minus alpha minus 2 from this term. If we combine alpha plus 1 minus alpha minus 2, we get 3. The alphas conveniently drop out. So the answer is 3 times alpha minus 1, which we recognize as 3 times alpha to the 2 falling. So to summarize, the forward difference operator evaluated on alpha to the 3 falling is 3 times alpha to the 2 falling. For those of you who have studied calculus, I hope this rings a bell. It should look like a very familiar formula. For completeness, let's have a look at what happens if we apply the backwards difference operator to the same lowering power. So del acting on alpha to the 3 falling. What does the backward difference operator do? It takes the polynomial evaluated at alpha and subtracts the value at alpha minus 1. Okay, so there's alpha to the 3 falling. We've already seen that before. Now we have to subtract alpha minus 1 to the 3 falling, which is alpha minus 1 times alpha minus 2 times alpha minus 3. Again, there's a common factor. The alpha minus 1, alpha minus 2 is common in both. And again, the other terms are alpha minus 3. They conveniently simplify to just give us 3. So there's the result, 3 times alpha minus 1 times alpha minus 2, which we recognize as 3 times alpha minus 1 to the 2 falling. It's not quite as nice as this formula, because the alpha to the 3 falling turned into an alpha minus 1 to the 2 falling. This is a little bit preferable, and we're going to use this one more than we use this one. So the forward differences of lowering powers are simpler. Now, for completeness, we also need to look at what happens when we apply these two operators to the raising powers. Let's do that too. Okay, so we're going to now have a look at what happens to the raising powers when we apply the forward and the backward difference operators. So there's alpha to the 3 raising. And we're going to apply the forward difference operator to it. What does the forward difference operator do? It says evaluate this polynomial at alpha plus 1 and subtract the value at alpha. Okay, what is alpha plus 1 to the 3 raising? It's alpha plus 1 times alpha plus 2 times alpha plus 3. We go up for the raising operators. While alpha to the 3 raising is just alpha times alpha plus 1 times alpha plus 2. You've established the pattern now, I hope. Alpha plus 1, alpha plus 2, they're common in both expressions. The other terms are alpha plus 3 minus alpha. They simplify to 3. So we're getting 3 times alpha plus 1, alpha plus 2, which is 3 times alpha plus 1 to the 2 raising. That's again not that simple because the alpha there turned into an alpha plus 1. Now let's take the raising power and apply the backwards difference operator to it. What does that mean? It means we evaluate it at alpha and we subtract the value at alpha minus 1. Alpha to the 3 raising, there it is, alpha plus 1 times alpha plus 2. Alpha minus 1 to the 3 raising is alpha minus 1 times alpha plus 1. These simplify because there's a common factor of alpha times alpha plus 1. The other terms are alpha plus 2 minus alpha minus 1, which simplify again to 3. And alpha times alpha plus 1 is just alpha to the 2 raising. So this time around we see that the backward difference of raising powers is simpler. On the previous sheet we saw that forward differences of lowering powers are simpler. Now backward difference of raising powers are simpler. And although we've just worked it out here with 3s, you can do this for 4s or 5s or in fact general n. And here are the corresponding formulas. They're good exercises for you to do. That if you take a lowering power, alpha to the n lowering, apply the forward difference operator to it, which is simpler than the other one, you get n times alpha to the n minus 1 lowering. And conversely, if you take the raising power alpha to the n raising and apply the backwards difference operator to it, then you get n times alpha to the n minus 1 raising. So the moral of the story is that both of these operators act just like the usual derivative, except that they don't apply to ordinary powers they apply to either lowering powers or raising powers, depending which one of these operators you're particularly interested in. So if you're interested in forward differences, then you should work in the framework of lowering powers. While if you're interested in backwards difference, then raising powers might be more convenient. And to make this sort of sensible, we should also define alpha to the 0 lowering and alpha to the 0 raising to be 1. To sort of be consistent, the endpoints. This kind of analysis with sequence is maybe taught in a combinatorics course, but it's certainly not as familiar to undergraduates as it could be and probably should be. These are actually very beautiful and elegant and simple formulas that will allow us to obtain almost spectacular results on sequences, and they really allow us to understand sequences in kind of a calculus kind of way. So it makes sense now for us to introduce some new bases for our favorite space, P3, the space of polynomials of degree less than or equal to 3. Here is the standard basis, or the power basis, that we've considered quite a lot already. Just the ordered set 1 alpha, alpha squared, alpha cubed. Now we're going to introduce these other two bases, the lowering power basis, consisting of 1 alpha, alpha to the 2 lowering, and alpha to the 3 lowering. I don't say alpha to the 1 lowering because alpha to the 1 lowering is the same as just alpha. And the raising power basis, 1 alpha, alpha to the 2 raising, alpha to the 3 raising. Claim these are both bases of our space P3. This is a 4-dimensional space of polynomials. There are 4 elements in that basis. How do we see that these are actually bases? It means, how do we see that we can write any polynomial as a linear combination, say, of these 4, and in a unique way, so that these 4 are actually linearly independent? The key is simply to observe that the degrees of these are very easy to see. This has degree 0, this has degree 1, this has degree 2, and this has degree 3. This has degree 2 because it's alpha times alpha minus 1, which is of degree 2. So now an induction argument shows that if you take the first k of these, then you get a basis for p sub k. So for example, just 1 is a basis for p of 0, which is just the constants. These two together form a basis of P1, the space of polynomials of degree 1 or less. And now when we're adding this third one here, we're adding something of degree 2. And because we're adding something of degree 2 and we already have all of the elements of degree 1, it means we can express the alpha squared in terms of this one and the 2 previous ones. Similarly, when we add this one of degree 3, it means we can express alpha cubed as a linear combination of this one and the 3 previous ones spanning the space of degree 2. That's a rather general argument. Whenever you have a bunch of polynomials, the first one of degree 0, then the next one of degree 1, then the next one of degree 2, degree 3, and so on, that's always going to form a basis for the space of polynomials. So from now on, we're going to stick to the lowering power basis, and everything that we say can be translated and restated in terms of the raising power basis as well. So here's a major theorem, which goes back to Newton. If you take a polynomial p in P3, and you express it as a linear combination of 1 alpha, alpha to the 2 lowering, and alpha to the 3 lowering. So we have certain coefficients, A0, A1, A2, and A3. Then These coefficients are given by this nice compact formula. The kth coefficient is the forward difference applied to p k times, then evaluated at 0, all divided by k factorial. So when k is 0, we get this one. When k is 1, we get a1. K equals 2, we get a2. K equals 3, we get a3. So here, very explicitly, are the four coefficients. A0, the claim is that's just p of 0. A1 is the forward difference of p evaluated at 0. A2 is the forward difference of the forward difference of p evaluated at 0 divided by 2. And A3 is the forward difference applied 3 times to the polynomial, then evaluated at 0, then divided by 3 factorial, which is 6. Now the first one of these is kind of obvious. A0 equals p of 0. Why should that be true? Well, if you replace alpha with 0 here, you're going to get p of 0 on this side. And here, you're going to get 0. And in this term, you're going to get 0 because alpha to the 2 lowering is alpha times alpha minus 1. And so if alpha is 0, that's going to be 0. Similarly, alpha to the 3 lowering, when you replace alpha with 0, it's going to be 0 times minus 1 times minus 2. That's also going to be 0. So plug in 0 here, you're going to get A0 is p of 0. What about these other three? Why do they hold? So let's have a look. What happens to this polynomial when we apply the forward difference operator? A0 goes to 0. A1 alpha goes to just A1. And what happens to A2 lowering when we apply the difference operator? We get 2 times A2 times alpha 1 lowering, which is just alpha. And A3, alpha 3 lowering, that gets sent to A3 times 3 alpha 2 lowering. We're using that basic formula for what happens to a lowering power when we apply the forward difference. So altogether, we're going to get A1 plus 2 times A2 alpha plus 3 times A3 alpha 2 lowering. And now what happens when we apply the forward difference operator again to this expression? Well, the A1 is killed. The alpha gets sent to 1, so this becomes 2A2. And the alpha to the 2 lowering is sent to 2 times alpha to the 1 lowering, or simply 2 times alpha. So this 3 is then multiplied by 2 to give us a 6. We get 6A3 alpha. Finally, when we do it a third time, this gets killed. 6A3 alpha gets sent to simply 6A3. And let's just make the additional observation. If we did another forward difference to this, we would then get 0. So all subsequent forward differences, in this case, are 0 because the polynomial is of degree 3. Alright, so now we can read off what happens when we substitute alpha equals 0 in these formulas. If we put alpha equals 0 in here, these two terms disappear. Now we get forward difference of p at 0 is A1. That's exactly that formula. Plug alpha equals 0 in here. Then that disappears, and we'll get A2 equals the second forward difference of p evaluated at 0 divided by 2. That's that formula there. And plug it into here. Well, there's no alpha on this side, so we just get A3 equals the triple forward difference evaluated at 0 divided by 6. That's our formula there. So that's a proof of this very fundamental fact. Going back to Newton, so it's an important fact. We can see that the position 0 is playing an important role. And this is exactly the same kind of thing that happens in calculus. When you look at a Taylor series for a polynomial or a function, then the coefficients are evaluated in terms of the derivatives at 0. situation is completely analogous to that one. So let's now have a look at a specific example and see how this Newton formula works in practice. We'll look at the example of the square pyramidal numbers, and now we're going to start at 0 because we've learned that we should start our sequences at 0 for this difference calculus to work efficiently. So we're going to start the sequence 0, so that's the 0th term, that's the first term, the second term, and so on. 0, 1, 5, 14, 30. And here I've repeated the difference table that we had earlier. So we're just taking differences. Now this is a 1 representing the difference between 1 and 0, 4 the difference between 5 and 1, and so on. It's a table of first differences, for first forward differences. And then here's the table of second differences, third differences, and the fourth differences are all 0. Now Newton's theorem is telling us that the important numbers are the ones that are appearing first right here. They are the various differences evaluated at 0. So the 0th element in the sequence. And here's what Newton's formula tells us. That the sequence S that we're starting with as a polynomial is 0, that coefficient, times 1, plus 1 times alpha, plus 3 times alpha 2 lowering divided by 2, plus 2 times alpha 3 lowering by 6. There are no additional terms because all the subsequent forward differences are 0. If this wasn't 0, we would have to add another term here. That means we would be not working in P3. Alright, well, what is this thing? To evaluate this in a standard form, we need to replace these lowering powers with what they are in terms of just alphas. So alpha 2 lowering is alpha times alpha minus 1. Alpha to the 3 lowering is alpha times alpha minus 1 times alpha minus 2. So this is now an expression that we can evaluate just using algebra. Expand it all out, collect like terms, and after you've done that, even better, factoring it. Okay, factoring it ends up with this lovely expression. Alpha times alpha plus 1 times 2 alpha plus 1 all over 6. Now this is an important formula because this is an important sequence. And the reason it's an important sequence has a lot to do with this first line of differences, which you'll all recognize as being the sequence of square numbers. Square numbers are very important in mathematics, and this sequence here is basically being summed by the square pyramidal numbers. So let's make the following observation. That while 9 is the difference between 14 and 5, 14 is actually the sum of 1 plus 4 plus 9. Similarly, 30 is the sum of the first 4 numbers here. 55 is the sum of the first 5 numbers. Is that an accident? No, I don't think so, because we can see that this number here is going to be this one plus this one, because this one is the difference between this and this. So this one is this plus this. What about this one? Well, this one is the previous one plus the difference. But we just said the previous one is this plus this. So this one is actually this plus this plus this. And then the next one is the previous one plus the difference. So that turns out to be this plus this plus this plus this. So actually the general rule here is that what's occurring here is the sum of the first n terms here plus whatever this one started with. In this case, 0. So the fact that we found a formula for the nth term here means that in fact we found a formula for the sum of the first n squares. So here's that important formula that in fact goes back to Archimedes, that the sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. So for example, 1 squared plus 2 squared plus 3 squared, which is 14. When n is 3, you have 3 here, 4, 7. So 2 times 7 is 14. There's a generalization of what we've just done that we get by looking at a general sequence S and its first forward difference. Let's call that forward difference R. So suppose the sequence S starts with S0, then S1, then S2, and then S3, and that the forward differences are R0, R1, R2, and R3. What does it mean? It means that R0 is the difference between S1 and S0. It means that R1 is the difference between S2 and S1. That R2 is the difference between S3 and S2. Now suppose we try to unravel that and express the S's in terms of the R's. Well, we can't do that quite because there's a sort of an undetermined amount of freedom here. We don't have any control over the first element in the sequence. So S0 is just whatever it is. There's no information about what S0 is from here. However, once we know S0, then from this equation, S1 is equal to S0 plus R0. Then from this equation, S2 equals S1 plus R1. Well, that was S1, so if we add R1, then we get S0 plus R0 plus R1. From here, S3 equals S2 plus R2. Well, if that's S2, then we add R2, then we get the sum S0 plus R0 plus R1 plus R2. So in general, the kth element of the original sequence is the 0th element of the original sequence plus the sum of all the forward differences up to but not including the kth one. So to get the kth element here, you take the first or the 0th one and then you add all the forward differences together up to but not including the position that you're at. This is showing us that taking forward differences and summing are, in some sense, inverse operations. The situation is completely analogous to, in calculus, the differentiation and integration are inverse operations. Summation is like discrete integration, and taking a difference is like a discrete differentiation. So it's reasonable that that parallel be around. I hope that you've all seen a simpler formula, the formula of the sum of just all the numbers from 1 to n. 1 plus 2 plus all the way up to n is n times n plus 1 over 2. So now that we have a formula for the sum of all the first powers up to n, and a formula for the sum of all the squares up to n, it's natural to ask, what about the sum of all the cubes? Well, let's look at that sequence. It's an interesting sequence. We'll start at 0 as usual. There's the first cube. The second cube is 8, and so the sum of the first 2 cubes, or 3 cubes including 0, is 1 plus 8, which is 9. The next cube is 27, add that, we get 36. The next cube is 64, add that, we get 100. We can see that it's the forward differences right here that are exactly the cubes. The difference between this sum and this sum is this third cube. So let's complete this to make a complete table of difference by taking the differences between the cubes. 8 minus 1 is 7, 27 minus 8 is 19, 64 minus 27 is 37, and so on. We don't see a pattern yet, so we take another forward difference. 19 minus 7 is 12, 37 minus 19 is 18, 61 minus 37 is 24, 91 minus 61 is 30. Now we're starting to see a pattern. The pattern becomes even clearer when we take another forward difference. 18 minus 12 is 6, 24 minus 18 is 6, and so on. And then taking a successive forward difference yields all 0, and from then on all the forward differences are 0. So this is a situation where we've got forward differences to the first power, second power, third power, and fourth power. The corresponding formula of Newton tells us that to calculate the original sequence then, we should write it as 0 times the sequence 1, 1 times alpha, 7 over 2 factorial times alpha to the 2 lowering, plus 12 over 3 factorial times alpha to the 3 lowering, and now plus 6 over 24 times alpha to the 4 lowering. And there are no additional terms because all the next forward differences evaluated at 0 are 0. This is now an explicit polynomial that we can evaluate. Admittedly, with some work, we have to replace alpha to the 2 lowering with alpha times alpha minus 1. This one with alpha times alpha minus 1 times alpha minus 2. And this one with alpha times alpha minus 1 times alpha minus 2 times alpha minus 3. When we do all of that, expand it all out, simplify it, lo and behold, a rather pleasant, even remarkable factoring occurs. It turns out that it's a square. And it's a square of something particularly simple, alpha times alpha plus 1 over 2, which we recognize as exactly the formula for the sum of the first n numbers. What is it telling us? It's telling us that the sum of the first 5 cubes, say 1 plus 8 plus 27 plus 64 plus 125, is the same as the square of the numbers 1 plus 2 plus 3 plus 4 plus 5. That sum is 15. 15 squared is indeed 225. So we've had a good look today at some important techniques for understanding sequences that are too often left out of undergraduate mathematics courses. But I think it fits naturally into a linear algebra course because it's naturally connected with the idea of linear spaces and bases of them. Let's have a look at some exercises having to do with today's lecture. So they might be a little bit more abstract than usual, a little bit less computational perhaps. The first one is to prove these formulas that I wrote down. I showed you how to prove them for the case n equals 3. Please have a look to see if you can prove them for the cases n equals 4 and n equals 5. You might even be able to write down a proof for general n. Second exercise, find and prove the analog of Newton's theorem for polynomials of degree 4 or less, which we've already essentially used in that last example. Exercise 22.3, write out explicitly the lowering and raising power bases of P3. So write them all out to see exactly what they look like when you expand them out as polynomials. And do the same for P4. And finally, a bit of fun with some sequences. So here are 4 different sequences, and I want you to figure out what the next term is. Or better yet, find a general formula for the sequences. Now these particular sequences are all polynomial sequences, so they actually are generated by polynomials. Of course, not all sequences are. In fact, only a minority of them are, but there are quite a lot of them which are, and they're interesting. And it's very satisfying to be able to take one of these things, apply the techniques that you've learned today, and come up with a formula for the general term. Now, next time we are going to carry on with looking at these sequence spaces, which are quite interesting. There's some very rich combinatorics associated to the bases that we've been looking at, these lowering and raising power bases. And very interesting numbers come up when we ask the question about how we go from one basis to another basis. These numbers are called Stirling numbers, and they play a very important role in combinatorics. And they come out naturally by applying linear algebra ideas to these particular bases of polynomials. That's what we'll do next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.